I have here an air track. I can blow out air so that the object here starts floating. So we can make the damping very small by making it float. But if we lower the airflow, the damping becomes a little higher. I have a spring here with spring constant K, and I have another spring here with spring constant K. They both have spring constant K. And now I'm going to drive this here at extremely low frequency over a distance eta 0 at maximum. Eta 0 cosine omega t. What do you think the amplitude of this object will be at that very low? Yeah?
Half of the amplitude.
Very, very good. Very good. Not eta 0, but why is it half? Because we have two springs. So effectively the spring constant is twice that. Exactly. So if I go very slowly, you will see that this displacement here will be twice as high as this displacement. But what I really want to show you is they are in phase. This one will go to the right when this one goes to the right. Now comes the catch. I showed you earlier there's a steady state solution. In the beginning, the system doesn't like me. It hates me. It fights me. It doesn't like that omega. It wants to do something different, which is part of next week's lecture. And you will see that in the beginning. And so we have to be a little patient before my will survives. You ready for that? So I'm going to start now to drive the system at a frequency which is below resonance. I want you to see two things, that they go hand in hand, and I want you to see that see, you're going to very low frequency. I'll give you the amplitude here. This is twice the amplitude of the driver. Now it is here, the spring, and now the spring is here. So it's only this much is 2 eta 0. So eta 0 is no more than 3/4 of an inch. And now we're going to let that object be exposed to this driver. And we'll give it a little bit of time to recognize me. It takes a little bit of time to reach the steady state solution. Left for me and both to the right for me. For you, they're going now both to the right and going both to the left. Going both to the right and both to the left. Now, this was the amplitude, twice the amplitude of the driver. And when you look carefully here, it's less. It is that eta 0 over 2 that this gentleman immediately noticed, because we have two springs. So you see here, apart from the factor of 2, you see the delta 0, and you see that the amplitude indeed is half of the amplitude of the driver because of the two springs. Now we're going to resonance, omega 0, and now nasty things may happen. It may break. We have to give it time. You see what funny things it's doing? It's not in steady state yet. You have to wait. Just a little patient. Give it more time. Notice also that remember this is only moving this much. Look how much this is moving. I may not even be exactly at resonance, we can only do the best we can here. We may not be exactly at resonance. Oh boy, I'm close to resonance now. Oh yeah. Oh man, look at that. Ooh! Am I at resonance? I think I got it. And you see, they're neither in phase nor out of phase. Now you see the 90 degrees. And look at this teeny weeny little displacement here. And look what this man is doing. That is resonance. Remarkable. Ah, Marcos, where's Marcos? We hit it. Right on. Now I will oscillate it way over resonance, not way, but over resonance. First, we first have it, the system must first calm down. And now I will change the frequency above resonance so that now you will see the phenomenon that I discussed earlier, that the amplitude is very small. Again, we have to wait a little, look how fast it's going, and that then will go 180 degrees out of phase. Now, look, this is going this much, back and forth. And this one is not doing very much. Now, if you can't see it, I can. It looks like this. Can you see it? That's what 180 degrees out of phase is. Very clear.